Okay, so so far I don't think I've said the word black hole, and but all the things that we've learned this semester turn out to be extremely relevant to the behavior of black holes and the information paradox in particular. And with all the groundwork that we've laid, it's going to be pretty quick to see how that works. So today I'm going to go through that. And let me just start out by discussing what the information paradox is. A lightning review of the information paradox. So let's, it's much more general. We can consider a much more general situation than this. But let's consider, here's the Penrose diagram for formation of a black hole. What am I? Explain this in a minute. So what are we doing here? Well, we could make the black hole however we want, but for simplicity, let me imagine we make it this way. We send in some shock wave at v equals 0. And I'll use this a little later. So I'm going to write down the metric for this. We send in a shock wave at v equals 0 with a total energy m, and we find that this space-time geometry can be described by the Vijay metric 1 minus 2m, where m is the total mass of the shock wave, theta of v, where theta is 0 before v equals 0 and 1 afterwards, over r dv squared plus 2 dv dr. I'm writing this now in advanced coordinates, plus 2r squared gamma z bar dz dz bar. So we have flat space down here. We have Schwarzschild here by the Birkhoff theorem, or Schwarzschild up to a diffeomorphism. And they're joined along this shock wave. We create an event horizon. That is, we create a region from which no light rays can escape to infinity. And so this is a typical picture of classical black hole formation. But now, quantum mechanically, as we discussed last year in Physics 211, after you make a black hole, after a long time, it will evaporate. So we have a rather different picture, which I'm going to draw like this instead. We throw the shock wave in. We make a black hole. And then after a very long time, and we'll talk about exactly how long in a minute, the black hole starts to evaporate. It's a period of time which goes to infinity as h bar goes to 0. The black hole starts to Hawking evaporate, and it gets smaller and smaller, and eventually disappears altogether. And so Hawking did this calculation in 1974. We discussed it at length last semester in 211. And what the calculation naively reveals is that what's emitted here, the spectrum of radiated particles, is a black body spectrum. This is what the semi-classical calculation tells you, with the temperature given by the Hawking temperature, which is h bar over 8 pi m. Now, and moreover, the outgoing Hawking radiation doesn't have any information. It doesn't know. It's essentially a process which occurs outside the horizon, a pair production process which occurs outside the horizon, with a negative energy particle going in correlated with a positive energy particle going out to infinity. So it doesn't care what's inside the black hole. So according to Hawking's original argument, all the information that went into the black hole is lost. So we could have made this out of red matter or blue matter or green matter, and the geometry up here would be the same. The geometry would be the same, and the outgoing Hawking radiation would be the same. Now, to make this argument a little more precise, one invokes something called the no-hair theorem. And the no-hair theorem says that you make a black hole, and however you make it, in a rather short time scale, roughly speaking, the light crossing time of the black hole, it settles down to some stationary state. So there's no hair here. And it settles down to a stationary state that is characterized by the total charge q, the total mass m, and the angular momentum j. Now, okay, so and then from there on, that's all we need to know to compute the subsequent evolution. And moreover, since it settles down to, as was assumed, a unique ground state, then there is no way that the information about no place to store the information that came out of the black hole. Now, nobody ever really thought that this radiation was exactly thermal. It was always presumed that charge, mass, and angular momentum are exactly conserved. In other words, if you emit a quantum of Hawking radiation of energy delta E, the black hole must have energy, a mass less by exactly delta E after it's emitted. So and that was not thought to be a probabilistic statement. That was supposed to be thought to be an exact statement. In other words, it has always been, it's never been questioned that charge, mass, and angular momentum were exactly conserved in this process. And so there was supposed to be some sort of correlation in the quantum numbers of the black hole and the quantum numbers of the outgoing radiation. But now we see from what we've learned in this course that cannot possibly be true, that the only hair on the black hole is q, m, or j. Whenever you have a conserved charge, for every conserved charge, there must be one kind of hair on the black hole. Because after all, what's the argument that electric charge is conserved? Well, we take the total electric charge, we write it as the surface integral at infinity, and we can then write it over a slice down here before we make the black hole. For example, we could make a black hole which carries some charge. We can write it as a slice up here. We can write it as a slice up here. Or, more interestingly, we can write it as a slice which ends at the horizon of the black hole. And then we need an extra boundary condition that tells us that about the charge of the black hole. So this is just integrating by parts. We must get the same answer for any one of these slices. Now what we've learned in this course is that there is an infinite number of such conserved charges. And in general, so in particular, the fact that the incoming, so now we have an infinite number of q epsilons. And it goes for all the different conserved charges that we've talked about: superrotation charge, supertranslation charge, and the large gauge charge. So in our argument that the incoming q epsilon was the same as the outgoing q epsilon, we didn't care what happened in intermediate times. So it still has to be true, even if you make a black hole and let it evaporate, that, I mean, if you extend the surface integral by going to a slice down here, or you extend it by going to a slice up here, you don't run into the black hole, and therefore it still has to be true that q plus epsilon is equal to q minus epsilon. But we could also do something different, and that is we could consider evaluating this q over slices that end at the black hole. And clearly, just as as we vary this slice and let it end at different parts of the black hole, there will be different amounts of large gauge charge that pass through this slice. And it will vary, the amount of large gauge charge that passes through this slice will vary in a complicated way as we move the slice around. And therefore, it must be the case that, that black holes are also capable of storing this kind of charge. In other words, it can't be true that there is just there are only these three conserved quantities. There have to be an infinite number of conserved quantities. Just a second, Temple. Moreover, one of the things that we've learned is that there is no preferred, in general relativity, there is no preferred notion of angular momentum. There are an infinite number of generators of the BMS group that are on the same footing. You pick one definition of angular momentum, there are an infinite number of generators of the BMS group which differ by conjugation with supertranslations, which are exactly on the same footing as ordinary, as one another. So once you say the words black holes are characterized by angular momentum and BMS symmetry, it immediately follows that the black holes must be carry an infinite number of different kinds of charges. And these now, just as energy conservation forces a correlation between the energy of the outgoing quanta and the energy of the black hole, all these charge conservation laws, which we've been studying all semester, are going to force correlations, infinitely many correlations, between the outgoing Hawking radiation and the various charges carried by it and the various charges remaining on the black hole. Now, people were not so interested in these three conservation laws, or if you count this as three, I guess it's 5 conservation laws, because there's an infinite amount of information going, arbitrarily large amount of information involved in formation and evaporation of a black hole, and 5 constraints is not going to have 5 constraints which force correlations on the outgoing Hawking radiation with the quantum state of the black hole is not going to have a significant effect on how information flows in and out or distributed. But an infinite number of correlations is a different story, and so it's very interesting to try to investigate that. Temple?
Why does the space-time slice end on the horizon of the black hole? Because I would have thought the horizon is a part of the singularity, and you can easily just extend it into the black hole.
Sure. You don't have to end it there. You could extend it in, and then you could say that this portion of the integral, it ended there because it's a dicey thing to talk about the inside of a black hole. But yes, we could just take it right through the black hole, and we could say that the integral of the supertranslation charge over this is what we're going to call the supertranslation charge of the black hole. So we can think of the or the large gauge charge of the black hole either as an integral over a three-dimensional space-like slice like this, or we can think of it as a boundary integral at the horizon. Yeah, you can do it either way. Yes, Prahar.
So there is a time when you create the black hole and then the light crossing time before it settles down. So
Yeah.
there's some radiation that will come out also there. So the assumption there is that radiation does not carry a significant amount of these charges, so that most of the correlation is between the late time Hawking radiation and the most of the super translation or the charges are kind of carried away by the Hawking radiation, but not by the early time radiation.
Right. There's all kinds of transient stuff that happens here, but it settles down to a black hole. Actually, I was going to do that a little later, but let me do it right now. So the Hawking temperature, and let me give it as a little assignment, is h bar over m. And so the power radiated, right? So it goes to 0 when h bar goes to 0, and it goes down as there's constants here, but I'm ignoring them. Now the power radiated goes like, according to the Stefan, I don't know what it's called, the Stefan Boltzmann law, I don't know what it is. It's the area of the black hole times the fourth power of the temperature divided by h bar squared, which goes like, since this goes like m squared, this goes like h bar squared over m squared. Again, it goes to 0 as h bar goes to 0, and it gets less as the black hole gets bigger. And also, typically, the energy is of a typical Hawking quanta is of order the temperature, that is, the Compton wavelength of a typical Hawking quantum would be the Schwarzschild, would be the Schwarzschild radius. So I want you to look at that and to tell me what the time is the typical time would be for the first, how long you have to wait to see one Hawking quantum. I'll give you a minute. Okay, so the rate of emission of these quanta with this energy is dN dt is equal to the power, which is the dE dt, times dN dE. But dN dE is just 1 over the energy of each quantum. So that is h bar squared over m squared times m over h bar. So dN dt is h bar over m. So the time for one to come out is 1 over that, which is, so the typical time is h bar over m. So so we have to m over h bar. M over h bar. So we have to wait a time of 1 over h bar just to see one Hawking quantum, which means that the kind of classical period of the black hole is very, very long. And this turns on way later. And so we have a clean division, a very clean division. We're in the semi-classical approximation. We're expanding in h bar. We have a very clean division between the classical black hole formation and the onset of Hawking evaporation. And anything like what you were asking about, transients having to do with various kinds of radiation going out to infinity when you form the black hole, that will all have cleaned up and settled itself out in times which don't involve h bar. There's no h bar in those time scales. Okay, so so now we'd like to kind of make this more precise. How do we try to describe the charges? What are these contributions to the charges in the case? Yes, Shuhan.
I think I'm missing something very basic here. So I thought throughout the class we only defined the asymptotic symmetry at non-infinity. Like Q epsilon plus and Q epsilon.
Well, this would be scry minus plus, say.
Oh, I see what you're saying.
Right, but that raises an important point, because, so for example, when we wanted to discuss massive particles, it wasn't good enough to know the action of the large gauge transformations just at infinity. Well, even that's not quite true. There were two approaches. Massive particles don't go out to null infinity, so we had to somehow get beyond null infinity. And there were two papers on this subject, and one involved a gauge invariant treatment, and the other one involved just taking an explicit choice of epsilon in the interior and working it out. And of course, they gave the same answer. And the trick is to, if you're going to try to extend things into the interior, the goal is to find some gauge to work in which gives you a nice physical picture. For example, if we wanted to understand just global electric charge, the integral of the electric field, we can introduce any function epsilon. And suppose we have a bunch of charges here, and we write the integral of electric field at scry plus minus is equal to total charge Q. Then we can introduce any function epsilon, and we can write this as let's take a space-like surface sigma. We can write it as the integral over a three-dimensional space-like surface sigma of, this is star f. We can write it as d epsilon wedge star f plus epsilon star d star f, which is just, of course, the matter electromagnetic current, the dual of the electromagnetic current J. where epsilon is absolutely any function that goes to 1 at infinity. This is a true formula for any epsilon. We could choose epsilon to vanish at some charges and not at others, so that maybe some of the j's would contribute and others wouldn't. But in this case, clearly it's a good idea to choose epsilon to be constant everywhere. And then we have a expression which is equally as correct as all the others. It's just equal to the integral of star j. But it gets us a better idea of the local physics. Now, ultimately in quantum gravity, the metric fluctuates. And local physics probably is not well defined. So ultimately in quantum gravity, in anti-de Sitter space, we've learned how to describe things in anti-de Sitter space precisely by looking at behavior near the boundary. And sometimes we venture inwards using various kinds of gauges and approximations, and we get interesting approximate physical pictures working in the semi-classical approximation. And so that is how we're going to proceed now. All right. Yes. Right, right.
But I mean, those boundary conditions, they came basically from analysis which was forbidding formation of black holes, right? They were trying to prove stability of mid-cosmic space. So how do you know if you have something like really big and nonlinear like this happening that you radically?
Well, I think we're just going to, we're just going to define the system. If there's something big and nonlinear happening in the middle, it shouldn't have much, it shouldn't look very different way out at the boundary. There's no reason to think that, there's no physical reason to think that something big and nonlinear in the middle is going to lead to radically different kinds of fall-offs at the boundary. I mean, the long-distance metric from the sun is no different than the long-distance metric from Schwarzschild. So it's going to be our working assumption that that all these matching conditions and so on can still be used when we have a black hole formation and evaporation. If we don't assume there's some kind of matching conditions, I mean, we just don't have a theory. That would be, what you're asking me is, how do we know that there is a theory? Well, okay, we could take the point of view there, it's our goal to find a theory. This seems like a sensible assumption, and there doesn't seem to be any other sensible assumption on the table. Okay, so I mean, I got a different version of that question that I've been asked is, symmetries imply conservation laws only if you have unitarity. So I'm not proving here that information is, I'm assuming here that there's some unitary, I'm also assuming unitarity, right? I'm not trying to prove unitarity. I mean, nobody can ever sort of prove that there isn't some crazy thing that happens in the middle of the space-time that violates unitarity, and you can't prove that you can't prove that there's no possibility for such a thing to happen. The way to proceed is to make some reasonable, plausible set of assumptions and try to build a consistent theory. Okay, so now let's go back now. I'm going to turn off black hole evaporation now, and I want to go back up to this picture on top and ask what happens to our charge conservation law. Well, so what we had before, see if there's any colored chalk here. What we had before was we had a q epsilon minus, which we wrote as an integral over this. And we used the fact, when we were only discussing massless fields, which we're going to continue now to, we could add massive fields to this, but it's just going to complicate the discussion. When we only have massless fields, we knew there was no boundary down here at I minus, because we know that for massless fields, to specify all the Cauchy data, it suffices to specify what they're doing at null infinity. You don't need to, they disperse, you don't need to give additional data about what is happening at this point. So that means we can just write as an integral over scri minus, and there's no boundary term up here. Now, when there were massless fields going down here, or going up to scri plus, there was an extra boundary term. And we had a long discussion of that boundary term, and we did the hyperbolic slicing, and we showed that, that the boundary term gave us the right term to give the massive, to reproduce the Weinberg-Soft theorem for massive particles. So clearly, now let's look at q epsilon plus, and let's extend it up this way. Well, clearly, we're not going to have q. So let's write it as a volume integral. So we have q epsilon plus is going to equal to q epsilon over scri plus. But clearly, that is not going to be equal to q epsilon minus, because scri plus is no longer a Cauchy surface. We need to close this surface to use Gauss's law. And so we're going to get an extra term over this surface, which I'm going to call the horizon H. If we don't have any massive particles, there's no contribution from stuff sneaking up there. In other words, the mathematical statement is that for massless fields in a black hole background, the future horizon and null infinity are a Cauchy surface. Okay? So we need to add another term here, plus q epsilon h. And this is going to be equal to q minus epsilon. So already this equation says that the conservation law tells you that, it's just telling you that the large gauge charge has two pieces, one that goes out to null infinity and one that goes into the black hole. So what is this QH epsilon? Well, QH epsilon is equal to 1 over e squared. The integral, we can write it in two forms. We can write it, let's call, this is the horizon H. And this surface up here, sometimes I call it DH, or sometimes I call it H plus. I don't know, somehow today DH, the boundary of H, sounded like a better term. DH, the future boundary of the horizon, of epsilon star f. But we can integrate that by parts and write this as 1 over e squared, the integral over the horizon, the full horizon, of d epsilon wedge star f plus the integral plus star j matter. Now, in what I've drawn here, I really would like some colored chalk. In what I've drawn here, we're also going to consider, so this is v equals 0. We could also consider at some later time sending in some charge current J. Okay, we could consider that kind of configuration. And then we would get this extra term. Now, what is this term here? Well, if we take epsilon to be constant along the horizon, then, in other words, along the null generators of the horizon, then this is tangent to the two-sphere. And so this is the limit as omega goes to 0. So when we try to write the mode expansion in Schwarzschild or in Vijaya, we need to have modes on the horizon. In addition to, we need to do a mode expansion on the horizon, and there's a huge industry of studying this. And they have different frequencies in terms of the advanced time v along the horizon of e to the I omega v d epsilon wedge star f. And this would be a graviton of frequency omega. This would be the mode describing a graviton of frequency omega with polarization d epsilon. And since we're taking omega to 0, it's a soft graviton. So we can have soft gravitons on the horizon. They're exactly like the soft, or photon, sorry, this is a soft photon because we're doing electromagnetism. We can have soft photons on the horizon in exactly the same way that we can have them at null infinity. And then you can ask the question, in fact, this is a homework problem. Suppose we take QH epsilon and we compute the commutator with AZ, the gauge field, in advanced gauge, AV equals 0. So we have the symplectic form, which we can write as an integral over any surface. Before we started out with an expression for the symplectic form on any surface. We pushed it up to null infinity. But you can also push it up to this surface here. And then there's a contribution on the horizon. And in the homework, you're going to show that QH epsilon with AZ is equal to I dz epsilon. So there are large gauge transformations which act on the horizon. And this charge creates a soft, when we go to the quantum theory and expand this in creation and annihilation operators, this will create a soft photon on the horizon. And if you act on this space here with this operator QH epsilon, you will create a soft, it won't change the energy. It commutes with the Hamiltonian. We know that because we can write it as a boundary integral up here. But it will, for example, it's a photon, so it will change the angular momentum by 1 unit. So, so a black hole with a soft photon is different than a black hole without a soft photon. It's a different quantum state. That is QH epsilon. So let's call the state, the portion of the quantum state on this null surface here, the black hole state M. QH epsilon on M is equal to 1 over E squared. If we aren't sending it, in a moment we're going to send charges J in, but if we don't, we could have made a completely neutral black hole with neutral matter. So Q, H, epsilon, and M is 1 over E squared d epsilon wedge star F, acting on M, which is not equal to 0. It's the original state M plus a soft photon. It's not degenerate, has different, it's energetically degenerate, but has different angular momentum. Okay, so any questions about that? So black holes have an infinite degeneracy in the same way that the vacuum at Scry has an infinite degeneracy. So it's not true what you've been hearing since you were babies, that there are only a 3-parameter family of black holes. There's an infinite number of inequivalent quantum states of black holes. So to understand this better, so we might ask the question, how do we make physically, how would we make implant a soft photon onto a black hole? So let's study that. So what I want to do is I want to take this current JV in this metric, and let's, at some later time, after we've made the black hole, V equals V naught, let's throw this JV in, and let's take JV equals, just to be really explicit, YLM Z bar over R squared delta V minus V0. Okay, so the first thing is it's one line to check that this current is conserved. So what we're doing is we're sending in a shell of charge, and I'm going to work in linearized perturbation theory, and I'm going to neglect the back reaction of this on the geometry. It's not what we're trying to study right now. So we're sending in a shell of charged matter. But since it's YLM, the net charge is 0. If we had net charge here, we would have to talk about going from Schwarzschild to Riesner-Nordström. So we know we're going to go from Schwarzschild to Schwarzschild, and we can, in the perturbation theory we're working in, we can neglect the change in the mass. Now, if we look at the constraint equations at infinity, I need to describe a little better exactly what it is I want to do here. So the Maxwell constraint equation says that dV FVR2, that is the 1 over r squared component of the electric field, plus gamma z bar dz f z bar v 0 plus dz bar f z0 is equal to JV2 times E squared in the conventions we've been using. So JV2 is just the 1 over r squared component. So this is just equal to YLM delta of V minus V0. Now, there are many different ways to solve this equation, right? We've got three things on the right-hand side, FZB, FZ bar V. So basically, we're solving one equation for three variables. And so what I want to do is we could talk about all the different kinds of solutions, but the one that I think most simply illustrates the physics is where we insist that we solve this equation without any electric field. So that doesn't violate anything. In fact, we're about to explicitly write down that since the thing, we of course wouldn't be able to do that if we considered a shell with a net electric charge. But if there's no net electric charge, we can certainly solve this equation. And the solution is that AZ is equal to DZ sorry, let me write it as theta of V minus V0 dz E squared over L plus 1 YLM of ZZ bar. Okay, the spherical harmonics, of course, depend on our coordinate on the sphere Z and Z bar. Now, it's easy to see that that solves this equation because if we construct the FZV or the FZV bar, we're just differentiating, and AV I'm taking to be 0, we're just differentiating with respect to V, and that will turn this theta function into a delta function. And then we get the Laplacian dz bar on this stuff. But of course, by definition, the Laplacian on the YLMs just gives L over L plus 1. That cancels this factor. And so then we have, I guess there was an E squared here. OK? So I've solved this equation, and I've actually only written it out at large R, but it's not hard to see that, in fact, this is an exact solution at every R. Moreover, if we ignore this factor, this is obviously a pure gauge transformation. So F is 0 before or after the shock wave. And so we have F equals 0 here, F equals 0 here, and FVZ bar not equal to 0 here. Now, we sent in a complicated angle-dependent charge distribution, but we dressed it with photons in such a way that no electric field was produced. And so what this wave does, what this shock wave does that we've constructed it in this way, is basically it produces a gauge transformation. That is, the whole space-time, both null infinity and the black hole, are acted on by a large gauge transformation where this is the gauge parameter. OK. Now, moreover, if we now compute the integral, so we can write this as epsilon. This is the gauge transformation parameter. So now if we take the integral along the horizon of f dv of f vz, it will just equal minus, well, it will just be equal to minus dz epsilon. Yeah, including the e squared there. So this integral of fvz is non-zero. So when the integral of fvz is non-zero, that means that this thing is non-zero. So that means that there's a soft photon. A soft photon is another way of, I mean, okay, I wrote this in form language, but if I had written it in the other language, it would be d squared z dz epsilon f v z bar plus dz bar epsilon f v z. And so this f v z is now non-zero. OK. So this process implants a soft photon on the horizon. Now, any questions? Yeah.
So physically, why is it important that the angular momentum is non-zero? If I say that L equals to 0.
Well, I wouldn't be illustrating anything new. If I sent in a thing, just a shell charge, what you would find is that I would have to make F2 be non-zero, right? Because obviously then I would have to have a radial electric field. In other words, there would be an obstruction to solving this equation if the right-hand side didn't I can only set FR2 to 0 if JV integrates to 0 over the sphere, because this is a total divergence on the sphere. So I would learn that if I throw charge into a black hole, I get a charged black hole. I think we knew that before. So I wanted to just throw that piece away and study the new interesting phenomena, which is what happens when you have these angular dependent charges. Now, we could have done something different. And in fact, in my paper with Perry and Hawking on this subject, we do talk about something different, where you don't demand that FR2 is 0, but it will still be true. Let's see, how do I show this? Let's take this integral. Let's take this equation and integrate it from along the horizon from, well, it's actually minus 4m. V equals minus 4m to infinity. If I have one that's made by collapse in this way, of dv FVR plus dz bar fz bar zv plus dz fz bar v times gamma zz bar. I'm doing this at fixed z, so that has to equal, well, let me just write it as jv e squared. Now, by the no-hair theorem, so obviously this is a total derivative. By the no-hair theorem, before we do anything, of course, the electric field is 0. The beginning of the horizon down there, the electric field is 0. And by the no-hair theorem, if we haven't thrown in any net charge, the radial electric field has to also be 0 in the far future. In this case, I don't think one can write down, one can still try to solve the equations, but you can solve them in terms of Hewn functions. It's not quite so simple. You can't just write an analytic solution on the board. But it has the property that the electric field will decay in the far future. And so since this is just evaluated at the endpoints, we're integrating this dv, we can forget about this term. And again, we learn that the zero mode of f of av of the field strength of the transverse components of the field strength has to be non-zero when you throw the charge in. So we would have gotten exactly the same result, but we just couldn't have written the solution in such explicit form. Okay. So this is all. So far I haven't let the black hole evaporate. Now I'm about to let the black hole evaporate, but let me pause and see if there are any questions before I do that. Yes?
So in everything what we were doing like before this, dynamics and so on, we talked about large gauge transformation in infinity, and there it was that if you fix it at one point, then at the rest of the infinity, it's something physical. But here,
No, that isn't true. When we talked about massive particles, we had to extend it into the interior.
Right, but then still the choice of the gauge in the interior is arbitrary. It's making any gauge transformations in the interior, it doesn't change anything physically, right?
Well, I mean, for that matter, the only thing that matters is the value of the gauge parameter at scri plus minus.
Yes.
So we could have, for example, when we went up along null infinity, we could have let epsilon depend on v in an arbitrary way. And we would have gotten some formulas that were correct but not useful or illuminating.
I mean, so here you imply somehow that when you that this change in AZ somehow does something physically to the horizon of the black hole. That large gauge transformations on the horizon also do something physical.
Right. Though this equation is gauge invariant. The statement that there's a soft photon on the horizon of the black hole is gauge invariant. But to understand it in this nice simple way as a change in AZ induced by the shock wave, a large gauge transformation induced by the shock wave, I had to choose a gauge. And I extended the gauge in a simple way from scri minus up to the horizon that was adapted to this problem. In the most general situation, where you've got colliding black holes orbiting and there isn't going to be some nice gauge that is, going to enable you to get some simple physical picture of where things are, and especially if quantum fluctuations are strong. But it's useful to think about these simple situations and choose gauges in order to get some intuition for what is going on. Actually, it would have been very nice, and we tried to. Here we're using AV equals 0 gauge, which is natural if you want to talk about how excitations coming from scri minus affect the horizon, because those are the coordinates that naturally connect the horizon. But it would have been very nice to, let me just throw this out as an interesting problem. I thought that this harmonic gauge that Campiglia and Latta used led to a lot of interesting insights. And it would be nice to try to analyze this problem in harmonic gauge. And that would mean finding solutions of the Laplacian with various properties in Schwarzschild in harmonic gauge, which we spent some time trying to do, but might be doable. I don't know. But it certainly would be interesting to analyze it in other gauges, and there is a section in our paper where we discuss how you can see that you get the same results.
So just in any physical situation, this theta function would be smeared a little bit, so it's not going to be a pure gauge transformation. Like if you actually send a real.
You mean not a shock wave?
Yeah, I mean like in any real situation, it's going to be smeared a little bit, right? So.
Well.
It's just a step function.
Well, it could be something like this, but there could be physical situations in which the space-time is diffeomorphic to Schwarzschild, exactly diffeomorphic to Schwarzschild before and after that's not generic, of course.
I just don't understand how like making gauge transformations not at asymptotic infinity but on the horizon of the black hole does anything physical. Like I understand that like large gauge transformations at infinity they can be physical, but in the interior the whole just the definition of the gauge transformation doesn't really change anything.
Well, okay, if you don't want to choose a gauge, you have to kind of stop at the picture I wrote in the beginning. It's obvious that there must be some charges going into the black hole. You would, in your logic, you don't like the formula that the total charge, which is equal to the integral of star f at scri plus minus, is equal to the integral of the integral of the matter current. That's a formula which is true only in one gauge. The more general formula is, as I said, plus d epsilon wedge star f plus epsilon star j. Right? So we learned something by taking epsilon equal to a constant. We're expanding around some semi-classical picture. So if you're not going to choose a gauge, you're only going to be able to discuss the surface integral.
No,
If you want to, the minute you want to discuss a volume integral, you must choose some gauge.
No, I'm happy to choose a gauge. I just don't want anything inside to change if I make a gauge transformation only inside of the space time. Right?
I'm not making it only inside. The gauge transformation is everywhere above this line. Right? It's theta v minus v0. Okay, so now let's let the black hole evaporate. So what's a little funny about this is, okay, we have different black holes. So you might worry about the following thing. There's different kinds of black holes which differ by different number of soft photons. But how do we know, how could we tell from the outside the difference between them? Do they evaporate differently? And what I'm about to show is that charge conservation gives us a simple relationship between the evaporation out product of a black hole with a state m and black hole with a state m plus a soft photon. So how does that work? So let's now get back to this picture up there where we make a black hole, and let's make it with completely neutral matter so that there's no there's no J's around. And we make the black hole, and then after a very long time of order 1 over h bar, it starts to evaporate, and eventually it disappears. And certainly there will, in general, be charge going up to Scri plus. There'll be whatever. In the generic case, there will be charged particles going up to Scri plus. And now let's divide this picture in two on some surface US, which I'm going to take to be a time of order m over the square root of h bar after the black hole is formed. In other words, it's way, as h bar goes to 0, this is a very long time scale, but it's still way before Hawking evaporation is turned on. So the whole information paradox arises in this picture where you can separate classical black hole formation separate the formation evaporation into a classical formation stage followed by quantum evaporations. Okay. All right. So at this point, everything is settled down. And now I want to write the Q plus epsilon. And I want to write it in two ways. Let me call this Scri plus greater, and this Scri plus lesser, before and after the dividing line. So obviously, Q plus epsilon, if I take this Cauchy surface, I can write it as Q plus epsilon. I can write it as Q Scri plus greater epsilon plus Q Scri plus lesser epsilon, just dividing the surface into two. On the other hand, I could also do this. And let me call this H lesser. It's the proportion of the event horizon before this dividing time. And then I can write this as Q of Scri plus lesser epsilon plus Q of H lesser epsilon. And there's a little dividing piece here. But if this is a parametrically long time in h bar, I don't need to put, and I assume that everything is settled down and before the Hawking evaporation turns on. That is effectively the analog of this point here, and nothing is happening there. In other words, to approximation, which gets better and better as h bar goes to 0, H lesser and Scri plus lesser are a Cauchy surface for everything that comes before. And that's good enough for me since we're doing an expansion in h bar. OK, now, without even that approximation, well, let me come back to that in a second. So now let me suppose that I have some quantum state of the black hole, m, and I let the black hole evaporate, and I find that m on, which is a quantum state defined on h lesser, under time evolution goes to some outgoing state x out up here. Okay? Then it follows that if I take q plus, well, I guess if I want to make a complete state on this whole slice, I need to also talk about the quantum state here. But let's say I've done measurements to collapse this down to some pure state. And so in both cases, I need to take a tensor product with some pure state on scribe plus lesser. And so then I know that from this, since these are the same thing, that these two guys are equal in the sense that this will commute with the Hamiltonian, so that therefore q epsilon h lesser on M will therefore evolve to some q scribe plus greater on x out. Now, if I have made this black hole with neutral matter, then this object here essentially is the charge has no, this q epsilon has no charge matter contribution into it, and all it does is create a soft photon on the black hole. So this gives me an infinite number of deterministic relationships which relate the outcome, given the outcome of a black hole with a soft photon, without a soft photon, I have a deterministic formula, not a probabilistic formula for the final evaporative outcome of the black hole with one extra soft photon. And it's a different quantum state in a very explicit way. This will contain both hard and soft terms because in general I may have charged radiation going out there. So this tells us that indeed we can distinguish after we let it evaporate. These conservation laws implies that we can distinguish black holes which differ only by the number of soft photons on them. Okay, any questions about that? Okay, let's take our 5-minute break, and then I'm going to talk about super translations. Okay, so now I'm going to go through the same story for super translations. And this is work in progress with Hawking and Perry. And it's conceptually the same as for the photons, but somehow the indices have a way of proliferating. Okay, and you will do part of it as a homework problem. All right, now, so instead of sending in a, let me draw the picture again. And I'm just going to talk about the classical story here. And that argument would work the same way. So let's imagine that we could, by the way, be discussing in all of this, we could have had a somewhat more involved discussion where we had eternal black holes instead of making them, and then we could have eternal black holes which we then super translate with these or implement large gauge transformations on, but Yeah, somehow I don't like having white holes, so I prefer to do it this way. So we make a black hole at v equals 0 with some spherically symmetric wave. We could start with c equals 0 down here. And OK. So we make the black hole. And then at some later time, v0, we send in something more complicated. So what's the more complicated thing that we're going to send in? Well, let's take TVV, which is the incoming stress energy tensor with the R squared already scaled out, according to our earlier notation. Let's take that to be equal to, now, unlike in the case of a charge, here there is no escaping the zero mode. You can't send in a zero energy shock wave. You can send in a zero charge shock wave, which has charge moments, but there's no such thing. The laws of physics do not allow us to have zero energy waves. So I'm going to put in a mu, which is, and I'm going to have to separately keep track of it. So I have mu plus t of z bar delta v minus v0. So this is r squared times, where tzz bar has no zero mode, d squared z gamma zz bar t is equal to 0. In fact, I probably want to assume that it has no L equals 1 mode either. OK. Now, the constraint equation. And as before, I'm going to linearize. In fact, it's an interesting thing. It's probably possible, and people have done things close to this, it's probably possible to analytically solve for a finite nonlinear solution corresponding to a shock wave that generates a supertranslation. But exactly that formula doesn't seem to be in the literature anywhere that I know of. But in any case, in this discussion, I'm just going to, I mean, electromagnetism is linear. So as far as the electromagnetic field here, it could be, I could make it, you know, the fact that I was linearizing wasn't important. But anyway, I will continue to linearize here. So this will be a small shock wave, and I will linearize in the metric perturbations. And under that situation, the constraint, I can't just send this in. I have to excite the metric. I have to obey the constraint equations. So I have that dv m bondi is equal to 1/4 dv of this stuff we've been discussing, dz squared czz plus complex conjugate. These are the soft graviton terms. And then plus this guy, mu plus t zz bar delta v minus v0. Now, MB is, to this problem, what the radial electric field FRV was to the previous problem. And there I just said, I want to solve this with the radial electric field equal to 0. But there's an obstruction to doing that, the analogous thing here. So I am going to just assume that MB, but I'm going to do the next best thing, is that MB in this region, well, I guess MB is, first of all, before we put in the thing, it was theta v times m. But now I'm going to, let me forget about, let me just write formulas that are valid after v equals 0. So MB is equal to m plus theta of v minus v0 mu. And so then, when I take dv, this turns into a delta function. this cancels this, and I need to solve dv, oops, I need to solve, well, I want to find a solution with the property that dz squared czz plus complex conjugate is equal to minus 4 tzz bar times theta of v minus v0, so that when I take dv of that, the remaining terms cancel. So this is the analog of what I did before. And the solution is czz. Now I'm just out at infinity now to leading order at infinity, is minus 2 theta v minus v0 dz squared of c sub t, where I'm putting the subscript t on here because this c sub t is equal to a Green's function convoluted with t, the source, Green's function convoluted with t of zz bar, where the Green's function is the solution of a quarter on the sphere, d squared plus 2, g of z bar w bar is equal to delta squared z minus w. And now you see why I need to have t not have an L equals 0 or an L equals 1 mode, because you can't invert this equation if there's an L equals 0 or L equals 1 place. And this Green's function has come up before in Sasha's lecture on gravitational memory. This is the Green functions that related the stress energy flux out at infinity to the BMS transformation that enters into the gravitational memory formula. So there's some explicit formula for it in our paper in terms of logs and products of z minus w. Okay. Now, this thing is, I've only solved it here out at infinity, but you can solve this problem at the linearized level for every r. Notice that out at infinity, all that's happening, this is a supertranslation for v greater than v0. So basically, you're joining along the shock wave two geometries which differ by an infinitesimal supertranslation. And where the supertranslations are given by, for finite r, in BMS coordinates are given by an arbitrary function, d by dv, plus 1 over r dA f dA. These are the infinitesimal vector fields, minus 1/2 d squared on the sphere f dr. And the supertranslation that joins the region above and below v equals v0 is just f equals ct. Now, this I've demonstrated here. I've made sense of this here only at infinity, but one can extend this to finite r, and you will do so in the homework problem. And one gets something a little, the extension is more complicated than an electromagnetic case, and one finds that HVV is equal to theta of v minus v0 times 2 mu over r. That's just the statement that the bonding mass is shifting. This is the linearized perturbation in the metric produced by the gravitational shock wave, minus m d squared ct over r squared, and hzz is theta v minus v0 minus theta z0 2r dz squared ct. So this is all very explicit, and hvz is equal to theta of v minus v0 dz 1 minus 2m over r plus a half d squared ct. So it's obvious that h is 0 before the shock wave, of course. The shock wave causally sources h. What's not obvious, but what you will show in the homework, is that that with an appropriate stress energy along the shock wave, that this h is produced, sourced by the shock wave, and moreover, that this h is pure supertranslation. In other words, this h is the Lie derivative of the metric with respect to this vector field with f replaced by ct. So it's just like the electromagnetic case. We throw in a shock wave, and above the shock wave, the whole space-time, including the black hole, gets supertranslated. And also we can see that the integral from minus 4m to infinity along the horizon dv of dv hzz, which is a soft graviton, this is on the horizon, is equal to minus 4m. It's basically this change here. These two terms cancel. Minus 4m dz squared ct. So such a shock wave implants a soft graviton on the horizon. It creates a shift in the transverse components of hzz before and after the shock wave arises. Now finally, as one closing comment, let me say that one of the nice things about the gravity case, there's a nice feature that happens. In the gravity case, one can already distinguish the different black holes by classical charges, classical superrotation charges. Now, the supertranslation group itself is an abelian group. So if you take a black hole and you act on it with a supertranslation, the new black hole doesn't carry a supertranslation charge. However, the supertranslation charges don't commute with the superrotations, which we studied 2 lectures ago. What are the superrotations? Let me just remind you that they are vector fields. I won't give the full extension into the interior, but on scri plus, or actually we're interested in scri minus here, they become dA, or let me complexify them, dzyz over 2 v dv plus yz dz, and the real and imaginary parts of this are super boosts and super rotations. The superrotation, the conserved superrotation charge, which we discussed several lectures ago, is 1 over 8 pi g integral scri minus plus, this would be at the bottom, d squared z, y z bar, and z, where this is the angular momentum aspect, the 1 over r term in the expansion of, in the coefficient of du dz in the line element, plus v dz times the bonding mass aspect. And now, under a super translation, you can show that delta, let me call it delta ct. So after the shock wave, nz will be shifted by super translation. Yeah, in fact, it's the 1 over r term there is 3m dz ct. And so this all becomes equal to 3 over 8 pi g integral d squared z y z bar m dz ct. In other words, when you super translate a black hole, already at the classical level, it gets non-zero super rotation charges. Yeah. So unlike the electromagnetic case where the charges were, the effect was to introduce phases which could only be measured in quantum experiments, here we actually see that the actual superrotation charges of the black hole are changed classically under super translation. So the conclusion is that despite what people have been saying since the 60s, black holes have lots of hair, both classical and quantum. The no-hair theorems tell us that there's only a 3-parameter family of solutions up to diffeomorphisms, but not all diffeomorphisms are trivial. And so there's a rich family of black holes. And in order to understand black hole information, we certainly need to understand the properties of this hair. So that, I think I will stop there. Any questions?
Were
Yes.
there quantum null hair theorems before as well?
Well, there was some discussion of quantum hair, and there are various kinds of quantum hair that a black hole can carry in special circumstances, like where you have discrete gauge symmetries or B fields or so on that can be measured by quantum. But all the previously discussed types of quantum hair, again, there was some small finite number. Just like, in more general theories, there can be more types of electric or magnetic charges that black holes can carry, but they were usually some small finite number, and there was some additional small finite number of types of quantum hair. But the infinity of classical and quantum hair is a new thing. Yes.
Wasn't it the case that there, in ADS3, there's supposed to be an infinite number of Virasoro conserved charges associated with black holes? Would you say that this is completely different than that case?
You could draw analogies to that case. Yeah, you could draw analogies to that case. I mean, there's certainly a lot of similarities in that those are the things that you're talking about are large diffeomorphisms. Yeah. Yeah.
When we were like writing down the constraint equation, say in the for the asymptotic symmetries in QED, like we use a large R expansion and impose boundary follow-up conditions to
Yeah.
write down the constraint equations order by order. But now that we're on the horizon, we're no longer taking R to D infinity, right? Do you have to impose some sort of new follow-up conditions?
No, it's a calculation that you have to do to show that that I didn't do, but it's not very hard to show that it's just some powers of R, and that the thing that I wrote down solves the full Maxwell equations for every R. Yeah.
So just to follow up on the previous question about ADX3. So yeah, I mean even there is an information problem, right? I mean in the sense that if you look at correlators, they would I mean thermal correlators would have a follow-up. Maybe so. If the infinity of charges do not solve the information problem, there how does one look to address the same problem in the flat space case?
Well, first of all, it's not true in ADS that there are. I mean, I think that first of all, there is no sharp information problem in ADS because black holes don't evaporate. And therefore, there are some adaptations of, it doesn't take the same sharp form in ADS that it takes in Minkowski space, where it's a sort of order 1 problem, right? The leading term in the information is not matching with our expectation. You have to start talking about subleading corrections to correlation functions in ADS in order to see the information problem. And we've certainly learned a lot from ADS, but it is a context in which the information problem is hard to pose, and I don't think we've made a lot of significant progress on it. So I think it's time for a new approach. And certainly flat space is the most natural home for the information problem. And it is, while there's some similarities with the ADS thing, there are also differences. It is not true in ADS that there is an infinite number, that there is a large or infinite degeneracy of black holes at every energy level. Acting with the Virasoro algebras changes the energy. So if we keep the energy fixed, this observation is not relevant. Right, so it's hard to see any context in which all these different states of the black hole will matter. So I think the structure of this, while there's some similarities to ADS, it's qualitatively different. And moreover, its structure, which is appearing in a context in which the information problem is at its sharpest. And finally, it seems to, we've found a flaw in the argument that there's an information problem in flat space. So, two flaws really. One, the statement that black holes don't carry any hair. So we now know that they carry hair, and in some approximations and in some gauges we can get a perturbative description of what the hair is. That's what I did for you today. So the statement that black holes don't carry any hair is wrong, and now that we've understood that they do carry hair, we should try to understand how that hair affects the evaporation, not if the hair affects the evaporation, but how the hair affects the evaporation, because we know for sure that the evaporation process, if it's unitary, will conserve these charges. So somehow it must, so we know there's something wrong with the way we'd been setting up the discussion before. And the second flaw in the argument is that it was assumed that when the black hole evaporates, there's no place that the information can be stored, and it has to have all gone out to infinity. But now we know that there, in general, will end up in a different vacuum than we started out with, and the final vacuum state could be correlated with the outgoing Hawking radiation in such a way as to maintain quantum purity. Now, personally, my personal prejudice is I doubt that everything I've taught you in this course is qualitatively enough to solve the information problem. Certainly we need many things we need to understand better, and there will be new, qualitatively important new insights on the way. But I think we've turned the problem upside down and seen that the old arguments are wrong, and want to understand how things could be corrected, and along the way I think we'll learn new things. And I don't see an obstacle to solving the information problem through this, but neither do I think it's around the next corner. Right. So what would it mean to solve the information problem? I mean, I think we would have to do two things. My definition of solving the information problem. Number one, you have to have some computation which gives you the Bekenstein-Hawking entropy with the right number. And not a squiggly line, but with the number. And number two, you have to have some kind of way of computing the rate at which information gets returned to null infinity. So you have to be able to compute something, not just saying words. You have to be able to compute stuff. And we have computed some things here. There's a lot of concrete formulas that we've given here, and so yeah. And yeah. Okay, great. Thank you.